Hello, I'm Xiaowei. Welcome to the presentation of our paper, Guided Pluralistic Building Contour Completion. Thanks for your time. There are some archaeology site images at the bottom. As you can see, the building structures are destroyed and are incomplete. In order to reconstruct the footprints of archaeology sites, obviously, extra inputs are necessary besides what's visible in the author photos. The extra input could be either going to the field and uncovering hidden structures, or getting some guidance from human experts. Our work is aiming to provide guidelines about where to uncover so that we could reconstruct or complete the archaeology footprints with the least effort. Given one incomplete footprint shown in the first figure on the right, multiple possible completions exist. In this figure, we show three possible versions for the top incomplete structure. We propose to complete the footprints in an iterative manner by completing with certain priors at each step. This iterative manner is illustrated in the second figure. Our system is short for JPBC, and its pipeline consists of two components, a feature section component and a completion component. In feature section component, we use an entropy-based feature section model to indicate where in the image it would be most beneficial to perform an uncover operation. Our solution aims to reduce as much as possible the number of uncover operations and thus reduce user or archaeologist effort. Results show that usually fewer than 4 such pinpointed uncover operations are needed, which is significantly less than uncovering the entire area surrounding the former building. The second component, completion component, is an image completion network which can take as input the initial building footprint and any partial or fragmented uncovered sections from the first feature section component. Then it runs an iterative process. These are some steps how we propose a prior feature. Given the incomplete footprint A, we compute the distances from a sampled building dataset and find the average of the top matched footprints shown in B. Based on B, we can compute the information entropy to represent the uncertainty of the completion, illustrated in image C, together with a distance field shown in D, which encourages the network to explore regions with large ambiguity yet far from known structures. Together, we propose E. Here, we list the formulas to compute the information entropy, and we propose the location where we can obtain the most information gain, which are most beneficial to the building completion processing. For a traditional encoder-decoder based completion network, one-to-many ambiguity exists, shown in the right figure. In this figure, we can see the input might corresponding to many versions outputs. Our completion model takes the incomplete footprint and the prior feature as inputs to remove the ambiguity and outputs a more completed footprint. Below, we show our approach supports both single feature images and multiple feature images. Our initial dataset is based on Bosak Island. It is in Turkey. It provides a prime location for us to explore building contour completion task. To enable our guided pluralistic building contour completion approach, we generate a large synthetic dataset of building contours spanning the observed style of the building structures in the general region. After inspecting the subset of buildings already studied in Bosak, we kindly classify them into three types of buildings: single-shape building, split-shape building, and T-shape building. Those three types are shown in the right figure. In our current system, we focus on building walls and we define each style procedurally, yielding random building variations. Beginning with the complete and synthetic building contour images, we then progressively mask out portions of each building in such a way we can produce 7 levels or layers of incompleteness, with layer 7 being the most incomplete, shown in the figure. As you can see, the level 7 covers only like around 6% to 13% of the whole building. We show quantitative results on our synthetic dataset for our JPBC approach at 2 different threshold values, 16 and 32. Compared to the baseline, which is the red line, our model reduces the error faster and yields a final prediction with a smaller error. We also show the visual results of our approach for different levels, level 1, level 3, level 5, and level 7. And also, we show the results for different building shapes. Additionally, in order to demonstrate the progress of completion, we show the footprints completion behavior in completeness layer, layer 1, layer 3, layer 5, and layer 7. As can be seen, as the incompleteness layer increases, so does the number of iterations. For example, layer 1 only takes 1 iteration. However, layer 7 takes up to 3 iterations. The figure also shows our approach produces the most complete footprints, especially in the upper layers, compared to the naive completion approach. Furthermore, we compare our method JPBC to 4 recent methods, which are Pix2Pix, GLCIC, PIC, and Sketchbird. As you can see, our model outperforms previous state-of-the-art methods, both visually and numerically. We also use our method to complete images from the actual archaeology sites of Bosak Island. Those results are shown on the right. Our JPBC approach also accepts human-drawn sketches as input, and it can generate plausible and reasonable complete building footprints. However, our approach has some limitations. First of all, currently for styles outside of our assumptions, our approach gives only its best guess. However, theoretically, we could easily extend our synthetic dataset to support more shapes. Second limitation is that if the network mistakenly completes some structures that are not present in the real footprint, it might block the feature sections. And one possible solution is that we can take advantage of some GANs adversarial networks to solve this limitation. As a summary, our novel guided pluralistic building contour completion framework starts with as little as 10% of a building structure and completes the footprint within 4 iterations. We also show our approach significantly improves the performance as compared to different state-of-the-art methods. Our paper has some future work. First of all, we'd like to develop a learning-based feature section component in order to accelerate its performance. Also, we'd like to add more details to building footprints. For example, we want to add more details to doors and arcs, etc. Additionally, we like to extend to a full 3D inference, not only a 2D. And further, we also like to apply our approach to other archaeology sites and also other domains. For example, we want to try using our approach on complete the roads network and floor plans, etc. And for more details, we refer you to our paper, and thank you for your attention.